Welcome to today's Trane Engineers Newsletter live program. I'm Jeanne Harshaw, and today we'll discuss ASHRAE Guideline 36, High Performance Sequences of Operation for HVAC Systems. We'll start with a brief review of the history of Guideline 36. Then we'll talk about what is and what is not addressed in this guideline. We'll explain a few of the control sequences as examples, and then focus on hydronic plant sequences that were added in the 2021 edition. Finally, we'll discuss how to validate sequences that have been implemented correctly and how to ensure they are specified to increase the potential for successful project completion. To cover the topic today, we have three Trane application engineers, Tony Bruno, Scott Delo, and Sarah Hilden. Tony, can you get us started?
Thank you, Jeannie. Let's start with a little history of ASHRAE Guideline 36. This guideline was created to fill a gap in how projects get designed and executed. ASHRAE standards such as 62 and 90.1 promote several optimization strategies like duct pressure reset and demand control ventilation, but do not provide the detailed sequences of operation that are needed to successfully implement these strategies. This often results in the installing contractor delivering an installation that doesn't align with the vision of the specifying engineer. In 2014, the ASHRAE Guideline 36 Committee was created in anticipation of the publication of Research Project 1455, which investigated and described high-performance sequences for VAV systems. This research project was published in 2015 and became the foundation for Guideline 36. The guideline was first published in 2018 and is currently in continuous maintenance. The most recent publication was in 2021. The goals of the guideline are described in its purpose. When adopted at scale, the guideline has the potential to reduce inefficiencies in how HVAC control systems are designed, installed, commissioned, operated, and serviced. The guideline aims to reduce engineering time by providing uniform sequences that can be specified confidently, which can result in reduced programming and commissioning time. Research projects have shown the potential for significant energy reduction with the implementation of these sequences. Scott will describe this more later. Finally, with the implementation of fault detection and diagnostic algorithms, equipment uptime and performance can be improved. The true efficiencies lie in manufacturers pre-programming and documenting the performance-based sequences described in ASHRAE Guideline 36. When a designer specifies a Guideline 36 sequence, they can have confidence that the sequences they specify can be successfully implemented by installing contractors. An installing contractor, using manufacturer pre-programmed libraries, can focus on the parts of the project that need adjustment while having the confidence that the fundamentals of the control sequence have been tested and proven. In the future, the guideline will include functional performance tests. These functional performance tests, when complete, will provide clarity to installing contractors and commissioning agents to validate that the sequences, as implemented, meet the performance intent of ASHRAE Guideline 36. Next, Sarah will cover what's included in the guideline.
Thanks, Tony. Now let's cover what the rest of the guideline includes. And we'll start with the guideline's structure. It just so happens that the purpose and scope are the first two sections. Sections 3 through 5 are the meat of the guideline. For the most part, we'll be covering what's in the guideline. We just don't have time to get into all the details about how to apply it in an hour-long program. We start off with set points in Section 3. First come set points determined by the designer, like zone temperature and CO2 set points. Next, design supplier and fluid temperature set points, and design supply and ventilation airflow rates corresponding to 62.1 or Title 24 ventilation requirements. Economizer set points are included as well. Section 3 includes minimum and maximum values for several set points. For example, a minimum heating airflow set point can be applied for a VAV reheat terminal. This could be based on the minimum airflow for a given electric reheat coil in a VAV terminal unit. It also includes equipment characteristics. For example, minimum and maximum chiller lift, which can be used for head pressure control. Included also are design primary and secondary chilled water flow rates and number of pumps operating at design flow, to name a few. Section 3 also includes set points determined by the test adjusting and balancing contractor, such as minimum and maximum fan and pump speeds, correlating to the differential set points required to achieve design flow. Finally, information provided by the controls contractor are based on the field system, such as minimum signal required to achieve adequate airflow at a VAV terminal's minimum stop. Each of these variables are defined with specific names and include information on how to determine the proper value. Each section is organized in such a way that depending on the system type used or configuration of equipment, relevant portions can be retained or deleted based on the design parameters. It starts with airside systems and then moves into hydronic cooling and heating systems, along with fan coil units and general exhaust, including set points for system variations. As an example, shown here is a multiple zone variable air volume system with reheat in the terminal units. This is a simplified drawing that I'll build up as we walk through a few items. This system could employ an air handling unit as shown here, or a packaged rooftop unit. The airside is served by a chilled water plant with parallel chillers configured as variable primary flow, or primary only pumping as it's referred to in the guideline. There are headered variable speed chilled water pumps and constant speed headered condenser water pumps. We'll assume there's a flow meter in the primary circuit in this particular case. We'll come back to these in a bit. In section 4, the hardwired points are defined. This section is essentially a set of tables that lay out how each point is configured, whether it's digital or analog, and whether each point is required for implementation of sequences in the guideline. It also makes recommendations for the type of device to be used and to which control point it's connected. These are arranged by system type and reference the same subsection as in section 3. Set points include accommodations for the commissioning agent to place equipment into testable modes, unless it would impact the machine or present a life safety concern. Let's look at what's required in our example system to get an idea of how having this information is advantageous. This table is from section 4.2, which defines hardwired points for a VAV terminal unit with reheat. The table starts in the leftmost column with designations of R required, denoting those required to implement the basic sequences of control outlined in the guideline. Points listed with A are application specific. Within other tables, there are optional points denoted with O for optional. These may be included at the designer's discretion. The next column is the description of the point. These might be temperatures, damper positions, or airflows. Included also are control signals that turn equipment on or off, control pump or fan speed, or signals from devices in the zones. The next column, type, denotes whether the signal is digital or analog and whether it's an input or an output, always with respect to the controller. The last column provides guidance around recommended device types. Points that are application specific near the bottom of this table are denoted with an A in the first column. We don't have any optional points for this terminal type. There are similar lists for the air handling unit and for the hydronic systems. Let's see what those might look like. Again, our simplified airside system drawing of a VAV system served by an air handler on the roof, with just 2 zones represented in the lower portion of this slide. To simplify, we'll focus on a single terminal unit's points, starting first with those required to implement sequences from Guideline 36. As I populate this diagram, each point will be identified by its type, input or output, and whether it's analog or digital. From the table, we saw the required airside points include the damper position at the terminal unit, in this case, an analog output from the controller. Next, an analog heating signal from the controller to the terminal reheat coil. For hydronic reheat, this could control a valve on the hot water line. Next, we have feedback as an analog input from the differential pressure transducer reflecting airflow in the terminal unit. The last 2 points are discharge air temperature and zone temperature from the zone sensor, both analog inputs to the controller. Each of these 5 terminal points had an R in the table, meaning they are required to implement the basic sequences of control outlined in the guideline. Other application-specific points are denoted in the table with an A. If an occupancy sensor is used, a binary input to the controller informs of occupancy, or an analog input from the zone sensor can be applied for local user set point adjustments. These are at the designer's discretion to include. Local codes may require occupancy sensors for lighting control, or perhaps CO2 sensors are included where implementation of demand-controlled ventilation is a requirement. At the air handler, required controller outputs include supply fan start-stop and fan speed, along with economizer and return air damper positions. Additionally, outputs from the controller include a cooling signal to the unit. Coming back from the air handler, we have inputs to the controller for supply air temperature, duct static pressure, and outdoor air temperature, so that decisions can be made for proper control. There are also a few optional points included here for filter pressure drop, along with heating coil supply and mixed air temperatures. Application-specific points are included at the bottom of the table. For example, if there's a heating coil in the air handler, often used to temper supply air in cool climates, it needs to be told when to heat and may send its supply air temperature back. Circling back to our air handler on the roof, we can visualize those required points from the top of the table. Let's walk through them now. The air handler's required controller outputs include supply fan start-stop and fan speed, along with economizer and return air damper positions. Additionally, outputs from the controller include a cooling signal to the unit. Coming back from the air handler, we have inputs to the controller to monitor supply air temperature, along with duct static pressure for fan speed control as dampers open and close. Last, there's a point to monitor outdoor air temperature so that decisions can be made for proper economizer control. I think we'd all agree. This exercise certainly illustrates the advantage of factory-installed, wired, and pre-programmed controls. And those were just the required points for the air handler and terminal units. The same process applies to the chilled water plant, starting at the chillers, moving through the pumps and loops, and then on the condenser water side. We won't go through this exercise today for the entire plant. The process is the same. Let's move into the next section. In section 5, the sequences themselves are described. Now remember, this is a guideline, not a standard. The intent is to achieve the functional results. It's not a hard requirement that the implementations are used exactly, but if alternative logic is used, it should result in the same functional performance. Tony will talk about validation later in this program, where it is now and where it's going. These sequences use a retain-delete format to determine which sequences are required based on the system type. It's like a choose-your-own-adventure with a menu based on the system design. We'll go through some specific sequences a bit later. An important point to add: the sequences provided in the guideline meet the various control requirements specified in ASHRAE 90.1 and Title 24 for energy efficiency. They also meet the indoor air quality control requirements specified in both ASHRAE Standard 62.1 as well as those included in Title 24. The 2021 version of Guideline 36 references the 2016 versions of 90.1 and 62.1 and the 2019 version of Title 24. Now let's wrap up what else is there. Included at the end are informative appendices. The first, Appendix A, includes control diagrams for each airside and plant system type. Next, Appendix B includes abbreviations and acronyms used throughout the document. And of course, Appendix C includes descriptions of the addenda applied to generate the current version of the guideline. Now I'll turn it over to Scott to discuss a few sequences in more detail.
Thanks, Sarah. There are three key concepts in the guideline that might be different from what you're familiar with. First, while most traditional control sequences do have optimization strategies, Guideline 36 primarily uses trim and respond. Second, the guideline prescribes rules for automated fault detection and diagnostics, or AFDD. Lastly, hierarchical alarm suppression is a unique solution which suppresses less critical alarms based on its hierarchy in the system so the operator can focus on the most critical alarm. Let's start by looking at how trim and respond works. Trim and respond is a feedback loop control method used instead of the traditional proportional, integral, derivative, or PID loop control. It uses feedback from equipment unit controls to determine what changes should be made to set points or system operation. A properly functioning trim and respond loop will continuously hunt. A good way to think about it, the system is trying to balance energy efficiency with comfort. When comfort is met, the loop will trim to a more energy efficient set point until the loop receives feedback that indicates that comfort is no longer being maintained. Then, based on that feedback, the system will respond until comfort is met. The cycle then repeats over and over. Let's look at an example of how trim and respond works using duct static pressure optimization. Each zone or VAV box controller generates requests based on rules. In this example, a request is generated if the damper position exceeds 95%. Not all zones are necessarily equal. Some zones may be more critical or not important. So an importance multiplier may be used to weight the zones and generate more or fewer requests while using the exact same set of request rules. The system will ignore some of the requests before responding. This value is adjustable and allows the user to tune the system to be more focused on energy efficiency when ignores are set to a high value, or focused on maintaining comfort when ignores are set to a low value. Feedback from the VAV controllers are evaluated by the request rules to determine how many requests are generated. Each zone's importance multiplier is then applied to its requests, and a sum total of system requests is generated. If the number of system requests is less than or equal to the number of ignores, the loop will trim by subtracting the trim amount. If the number of system requests is greater than the number of ignores, the loop will respond by multiplying the number of requests greater than the ignores by the respond value. You should note that the system will always trim at a constant rate, but can respond dynamically based on the number of requests. This allows the loop to respond more quickly to satisfy zones when requests are high. A maximum response value is present to limit how much the set point can change, so an extremely high number of requests does not cause a dramatic set point change. Let's take a look at how this might work in an operating VAV system. This graph shows the time on the x-axis. The lower chart shows the number of requests on the y-axis, and the upper chart shows duct static pressure set point on the y-axis in green. In this example, the system becomes occupied at 8 a.m. There's a 10-minute time delay after the system is occupied. Since the run frequency is every 2 minutes, at 8:12, the system makes its first change to the static pressure set point. Since there are 0 requests, the system trims by subtracting the trim amount. The system trims again at 8:14 because the requests are not greater than the ignore threshold. At 8:16, the number of requests is greater than the ignore threshold. The system responds by taking the number of requests above the ignore threshold and multiplying that value by the respond value. In this case, there is one request above the ignore threshold, so the system responds by adding 0.06 inches to the static pressure set point. At 8:18, there are two requests above the ignore threshold, so the system responds by adding 0.12 inches to the static pressure set point. At 8:20, there are 6 requests, 4 over the ignore threshold, which would equal a response value of 0.24 inches. Since that is greater than the respond maximum of 0.15 inches, the system responds by adding 0.15 inches to the static pressure set point. At 8:24, the system requests drop low enough that the system starts to trim again. In this manner, the system continues to dynamically reset the duct static pressure set point throughout the occupied day. Next, let's go over the benefits of trim and respond. In comparison to traditional PID loops, trim and respond is easier for technicians and commissioning agents to tune the system operation. This is partially due to the fact that it can trim slowly and respond quickly. Both the trim and respond rates are adjustable and may be different, which is notable since PID loops move at the same rate regardless of direction. Since the system is receiving requests from each zone, those that may be having mechanical or maintenance issues are easy to identify. Trim and respond also adjust the importance of individual zones and may be used for many optimization strategies in both airside and waterside systems. Next, let's go over the second key concept, automated fault detection and diagnostics. AFDD is a sophisticated system for detecting and diagnosing control system faults. The goal is to identify sensor or mechanical faults before they become an issue for proper system operation or have an impact on energy efficiency. There are more than 15 different diagnostics identified in the guideline that apply to air handlers and hydronic systems. For each air handler operating mode, such as economizer or mechanical cooling, different diagnostics are run to proactively identify issues. Some examples of those diagnostics are temperature drop across an inactive cooling coil, temperature rise across an inactive heating coil, or discharge static pressure too low when the fan is at full speed. Next, let's go over the third key concept, hierarchical alarm suppression. As HVAC systems get larger and more complex, the number of potential nuisance alarms becomes a major issue for building operators. The guideline addresses this issue by using hierarchical alarm suppression. Alarms are ranked as source or load. If the source has an alarm, the load alarms are suppressed. For example, if a fan fails at the air handling unit, all zones served by that air handler will have their alarms suppressed. This reduces the number of alarms generated and allows the building operator to focus on the most likely cause of the alarm. Next, we'll look at how the guideline recommends controlling VAV boxes. Each type of VAV will have specific sequences and diagrams which show how they are recommended to operate based on the heating and cooling requirements. Single and dual duct VAVs are covered in the guideline, both with and without reheat, as well as fan-powered VAVs. VAVs with reheat are specified to use a dual maximum approach, which is shown in the image. This requires the VAVs have discharge air temperature sensors. Dual max is when the VAV has a maximum heating discharge air temperature set point. As heating is required, the box will open the hot water valve or modulate the SCR electric heat until the maximum discharge air temperature set point is reached. At this point, the VAV will start to provide more air while maintaining discharge air temperature. Particularly in cold climates, this prevents extremely high heating discharge air temperatures in spaces that have large heating loads. The lower discharge air temperature reduces stratification, improves comfort, and uses less energy. Next, let's look at air handler control. Similar to VAV boxes, there are many types of air handlers covered in the guideline, including dual duct VAV, multiple zone VAV, and single zone VAV. The guideline does a good job of providing several sequences that an engineer can select from based on the type of air handler. Different sections of the sequence are then removed based on which air handler is used. For example, there are multiple options for outdoor air flow measurement, building pressure control, and minimum ventilation. Sarah, would you take us through the updates in the most recent version?
Thanks, Scott. That's a great introduction. Now let's get into some specifics around the additions in the 2021 version of the guideline. In this version, there are now sections dedicated to chilled water plants in several configurations, including air-cooled and water-cooled chillers and hot water plants. Two other additions are fan coil units and general speed exhaust fans. Each system type has content within the sections we went through earlier, defining set points, hardwired points, and sequences for both airside and waterside. You can pick and choose the portions applicable to your particular design. The information in the guideline is not prescriptive. Its intent is to produce the outcome of a high-performing building, while at the same time reducing time spent on engineering, installation, and commissioning the system. Now that we have chilled water plant information, let's dive into a few sections, starting with equipment staging. The plant configuration we'll look at in more detail is piped for variable primary chilled water flow with headered pumps. The manifolded condenser pumps are constant speed. The diagram shows two chillers, but could be extended for a larger plant with more chillers, including a swing chiller. We'll touch briefly on that case in a bit. Other plant variation diagrams are included in the appendix, with associated sequences in Section 5, including pumped coils and waterside economizer, to name a few. Let's start with equipment staging. In general, equipment is staged in a lead-lag relationship or lead standby for redundant units, with timers to record staging and lifetime runtime. The staging runtime is used to rotate the chillers in the staging order and is user resettable. Lifetime runtime, on the other hand, is cumulative runtime and should be stored in a software point that is not resettable. The staging order changes while one or more identical equipment is running. Equipment is not actively shut down to equalize staging run hours. Rather, it moves to the back of the line when its run hours are the most, or in the event of an equipment fault. Equipment faults don't necessarily preclude operation, though. As an example, chillers and boilers may be turned off and sent to the back of the line. Towers, fans, and pumps continue to run, even if they're already last in the list, picking up as much load as they can. However, chillers and boilers not operating properly may prevent successful startup of lag equipment. For equipment that runs 24/7, the staging order can be adjusted at a specified time and day of week based on staging runtimes, of course, proving equipment is on prior to shutting down the previously operating equipment. This applies not only to heat moving equipment, but also to system pumps. Lifetime runtime is not used for staging, and here's why. For a plant with a vintage chiller, only newly added equipment would operate until its runtime exceeded that of the older unit. So how do we decide the staging order? The first thing to do is determine which chillers in the plant will operate within a given stage. Guideline 36 provides an example table shown on this slide to guide an engineer through this process. The example includes a smaller swing chiller, chiller 1, along with two larger chillers, chillers 2 and 3, which are assumed to be interchangeable. What does that mean? Typically that the chillers are equal in capacity and compressor type. With that said, it allows for the use of the OR statement in the staging table, enabling those chillers to be lead lag controlled per the aforementioned logic. Now, setting up the staging chart is often the more straightforward process. We know from experience that determining what has to happen and when it should is the more difficult task. This is where the guideline is helpful, in that it identifies at what point a transition should occur generically. When applied to a specific plant, it becomes clear at what point to start the transition. When to stage the plant up or down varies based on what's in the plant. If there are no flow meters in the secondary loop, the guideline directs to the use of Q required. This is calculated based on the measured flow in either the primary or secondary circuit, depending on configuration. In our example, we have primary only pumping, and there is a flow meter in the primary loop. Q required in tons is the primary flow times the delta T across the loads, which is system return minus chilled water supply temperature set point, divided by 24. On any staging event, Q required is held constant until the stage change is complete. This is to avoid instability during a transition when flow rate and temperatures change. We'll see in a bit how Q required impacts part load ratio, or PLR, and the downstream implications. This is different than for a primary-secondary plant, so be sure to reference the correct section when taking snippets. Once Q required is known, it's used along with the available stage capacity to determine the operating part load ratio, or OPLR, of the plant. This value is compared against the stage up PLR, or SPLR up, to determine when to go to the next stage. A similar value is used for staging down, staging part load ratio down. The equations for calculating the staging part load ratios are the same. However, because the stage adjacency differs, whether we are adding or subtracting chillers, the calculated values are not the same. We'll see those equations in a bit. Before we go there, we need to know which equations apply to various compressor technologies. Generally, positive displacement chillers, those with screw or scroll compressors, are staged on first. They're often lower capacity than centrifugal chillers, so are better suited for lower loads. Next, variable speed centrifugal chillers are staged on, and last come the constant speed centrifugals. Because fixed speed chillers are often the largest and last stage chiller in the plant, and their efficiency is more sensitive to load, their staging rules take precedence over the prior rules. When staging chillers up or down, the current stage's operating part load ratio is compared against the stage up part load ratio when adding chillers, or against the stage down part load ratio when subtracting chillers. A stage must be available in order to transition. To determine the operating part load ratio, divide the tons needed to meet the load by the total design capacity of chillers in the stage. The guideline also considers the minimum unloading point of the chillers, below which cycling would occur. This may be used during sequences of swing chillers to prevent cycling of the operating stage. Let's discuss staging up first. The staging part load ratios are based on compressor type in the current stage when staging up. When staging down, they're based on the next lower available stage. While positive displacement chillers are available with variable volume ratios, they're not always purchased with this feature. Their efficiency is impacted less at fractional lift or load. These chillers should be nearly fully loaded prior to deploying the next stage of chillers. In this case, the default is 80% loaded, but is adjustable for applications where chilled water temperature disruptions are less tolerable. because constant speed centrifugal chillers are often the largest and last stage chiller in the plant, and their efficiency is more sensitive to load, their staging rules take precedence over the prior rules. These chillers cannot slow their rotational speed, so they unload using inlet guide vanes, which means their efficiency degrades more at lower load points. For variable speed centrifugal chillers, the staging part load ratio is calculated as the 5-minute rolling average of the equation shown, sampled at least every 30 seconds per the guideline. Factors E and F include two new terms I alluded to earlier when I mentioned equipment capabilities. They consider lift minimum and lift maximum. Refer to the guideline for more details. Now, because centrifugal chillers need to avoid the surge region, they may need to speed up. This equation keeps the chiller out of surge by resetting the staging point up when lift is high to reduce throttling of surge control devices to keep them operating near optimal efficiency. There are fail-safes in place to look at chilled water temperature along with plant flow to stage on a chiller when required, even if the conditions shown are not met. And staging down uses the same staging part load ratio equations, but because the minimum operating part load ratio of each stage varies based on available chillers, it results in a different value than that of the stage up equation. Keep in mind, controls providers often have their own algorithms for staging chillers, which are often some variation of this methodology. Remember, these methods are a guideline, which is also why the staging part load ratios are adjustable. A designer may opt to not use these equations within their sequences, as the sequences are not prescriptive. What about pump staging? Different rules are applied based on the chiller and pump configuration. But since we've selected a variable primary flow configuration with headered pumps for chilled fluid, let's continue down that path. Chilled water pumps are staged as a function of chilled water flow ratio, the ratio of current chilled water flow to design primary pump flow for headered chilled water pumps in a primary only or variable primary flow system, as we often refer to it. Flow is used instead of speed to keep pumps operating near their most efficient operating point. The staging equations also consider the number of pumps operating at design flow and assume equally sized pumps. As the demand for cooling increases, the coils require more flow. The next pump is staged on when the flow ratio becomes higher than the number of operating pumps divided by the pumps in the manifold minus 0.03. For example, if there were 4 pumps in the manifold with a design flow rate of 1600 GPM total, or 400 GPM per pump, and there are 2 pumps operating at a point in time, the next leg pump would be staged on when the chilled water flow ratio becomes greater than 0.47, corresponding to 752 GPM of primary flow. Similarly, when staging down, the flow rate must be equal to or less than 752 GPM under that new condition, 3 pumps running, for 10 minutes to disable the last lag pump. The stage down flow ratio may be offset slightly lower than the stage up point in order to avoid cycling between pump stages, especially in applications with loads that are highly variable. There are other equations used for different pumping schemes, so be sure to validate the configuration when using parts of the guideline. Now I'll turn it over to Scott to discuss chilled water reset.
Thanks, Sarah. Whenever the system resets a set point, there must be a balance struck between how the reset affects the energy consumption of several components of the system. Let's use chilled water supply temperature reset as an example. A low chilled water set point uses more chiller energy, but often uses less pump energy by making the coils more efficient. On the flip side, a high chilled water set point uses less chiller energy and more pump energy. In this case, the guideline recommends resetting the chilled water supply temperature first and the pump differential pressure second. since the chiller compressor energy savings are greater than the pump energy increase. This may be counterintuitive, since traditionally pump pressure is reset first, and chilled water supply temperature typically remains constant or is reset based on outdoor air temperature. Let's look at an example of how this might work. In this example, we have a single 500-ton chiller selected at 40-degree chilled water supply temperature and a 58-degree return. The condenser conditions are 90-degree entering the chiller and 105-degree leaving. The variable speed primary pump is sized for 667 GPM and 60 feet of head. If the system is at 50% load and the chilled water temperature is reset, we may have a 49-degree supply temperature. The higher chilled water supply temperature lowers the chiller energy consumption significantly, but not the pump. This is due to the higher flow rate and lower delta T that is caused by the higher chilled water supply temperature. Next, let's look at what happens if we reset pump pressure instead of chilled water temperature. In this case, the chilled water supply temperature is still at 40 degrees, and we're maintaining the design delta T. This lowers the flow rate and pump power compared to the previous example. Unfortunately, the lower chilled water temperature increases the chiller energy consumption compared to the previous example. Let's look at how this impacts the total chiller and pump energy consumption. As shown in the table, chiller energy drops by nearly 23% when the chilled water temperature is reset, but pump energy increases by over 91%. Although the pump power increase is significant, total plant power drops by 32.9 kW or 21.2%. This example shows that in many situations, resetting chilled water temperature before pump pressure saves energy overall. Next, let's look at what happens when chiller plants are designed for low delta T's and high pump head. In this example, we have a single 500-ton chiller selected at 44-degree chill water supply and 54-degree return for a low delta T of 10 degrees. The condenser conditions are 85 degrees supply to the chiller and 95 degree leaving. The variable speed primary pump is sized for 1200 GPM and 150 feet of head. At 50% load and resetting the chilled water supply temperature gives a chiller plus chilled water pump power of 138.4 kW. There is some reduction in pump power, but is still drawing over 32 brake horsepower. When the pump pressure is reset instead of the supply water temperature, there's much more pump energy savings. In this example, the pump is drawing 11.4 brake horsepower, but the chiller is using a little bit more power. The chiller plus chilled water pump power is a nearly identical 142.8 kW. In this example, with a low design delta T and high pump head, resetting chilled water temperature first only saves 3.1% more power than resetting pump pressure. The guideline acknowledges this and recommends resetting both pump pressure and chilled water supply temperature together for chilled water plants that are designed for 12-degree delta T's or less and over 120 feet of pump head. Let's look at how applying ASHRAE Guideline 36 to existing buildings impacts building energy consumption and operating cost. Existing buildings present a unique opportunity for control optimization. Most existing buildings have had changes to how spaces are used over the course of their operation, and the control system may not be operating as designed. In addition to changes to the building usage, building codes and regulations are constantly being updated. Engineers and commissioning agents have an opportunity to address these issues when recommissioning a building using the sequences in Guideline 36. If the building already has an existing BAS system, the cost of implementing these sequences is typically low. To achieve the fastest payback, it's best to start by identifying the sequences that require the least number of additional controllers and sensors but have the greatest impact on energy cost savings. Not all systems need to be changed or updated for your customers to realize savings. There are several third-party studies that quantify the potential energy savings by applying Guideline 36 to existing buildings. The first study, published in the Journal of Building Performance Simulation, showed 30% energy savings versus a baseline of traditional control methods, modeled in Spawn of Energy Plus. The second study, done by Pacific Northwest National Lab, or PNNL, showed 29% energy savings when compared to poorly operating buildings modeled in Energy Plus. These studies highlight the significant financial savings opportunities for building owners that implement these sequences. Next, let's look at the results for an actual building. In this example, a hospital in Climate Zone 4A tracked their energy consumption and cost from 2018 through 2020. In 2019, they implemented the airside sequences from Guideline 36, including trim and respond. In January of 2020, they implemented the new control sequences for their hot water system. This building owner realized a 13% energy intensity reduction by making changes to only a portion of the HVAC systems in their building. Tony, would you walk us through how to validate that Guideline 36 was implemented properly?
Of course, Scott. Validating that these ASHRAE Guideline 36 sequences were implemented properly takes a relatively deep understanding of the intent of the guideline. Even though the guideline is written rather prescriptively, it specifically states that alternate implementations that meet the intent and performance are acceptable. It's important to keep this in mind when commissioning a project. For instance, the dual maximum VAV sequence shown here implies two control loops, one for heating and another for cooling. These loops control the VAV box through cooling mode, dead band, and 2 stages of heat. The first stage of heat is constant flow variable temperature, and the second stage is near constant temperature with variable flow. Manufacturers might choose to implement the same sequence with additional control loops to provide more granularity and better stability. This is a common technique to differentiate between the first and second stages of heat. Understanding more than just the raw text of the guideline is important to functionally test the sequences properly. There is work underway by the Guideline 36 Committee to create functional performance tests to aid in validation of the manufacturer pre-programmed sequences. In addition, functional performance tests will likely be created to validate sequences once installed. Until these are completed, it's best to work with your manufacturer or manufacturer's representative to understand their implementations. Communication between the designer, controls contractor, and commissioning agent is key to delivering an installation that delivers the performance that the building is entitled to. It is often helpful to ask for documentation or demonstrations. Where concerns exist, be clear as to your expectations and how the implementation will be tested for conformance. Now let's take some time to explore techniques for specifying these sequences. There are several approaches to specifying Guideline 36, each with advantages and disadvantages. One method we've seen is to use a single reference to the guideline, such as the VAV box shall be programmed per ASHRAE Guideline 36. This could become more viable as the guideline gains adoption, but is likely too vague right now. This method requires the least amount of work for the designer, but when specified in this manner, we can expect a number of requests for information, RFIs. In some cases, we might also have poor assumptions made by the installer, leading to an installed control system that does not meet the designer's intent. Another method is to include the entirety of Guideline 36 embedded in the specification book. This approach also leaves the door open for significant interpretation and confusion, much like the single reference. The projects where we've seen the most success are those that incorporate the parts of the guideline that specifically apply to the equipment and systems on the project. For instance, copying the language from the guideline that describes a specific air handling unit configuration removes the ambiguity that otherwise might exist. This method leaves less room for interpretation and contains only the relevant information. It also contains all of the information that the controls installer needs to successfully implement the sequence. Likewise, an engineer could choose to reference by number the specific sections of the guideline that apply to that air handling unit configuration. The downside of this approach is that it requires the extra step of the contractor finding the associated reference in the guideline document. Like with many things, spending more time up front to add the appropriate level of detail to the specification often results in a more successful project. With any of these approaches, it's helpful and important for the designer to draw attention to areas of the sequence that need to be customized for a particular installation. One technique we've encountered that has been proven to be successful is for the designer to use special font treatment to indicate where the sequence has diverged from ASHRAE Guideline 36. This helps the controls contractor and commissioning agent plan appropriately when approaching the project. There are some tools available to help in specifying ASHRAE Guideline 36. When the guideline is purchased, the purchaser receives a Microsoft Word version of the document that can be used to copy and paste guideline text into the purchaser's specifications and plans. There are also several free web-based tools, including Trane Design Assist, that can be used in the creation of specifications using ASHRAE Guideline 36 concepts. It's recommended that designers purchase a copy of the guideline before using these tools. I'll turn it back over to Scott to summarize.
Thanks, Tony. In summary, Guideline 36 provides flexible, code-compliant sequences of operation for engineers, commissioning agents, and building owners. Optimization in the guideline is based on trim and respond. The guideline now provides sequences for both airside systems, chilled water systems, and hot water systems. Studies have proven the potential for energy savings by implementing these sequences, and they are applicable to both new and existing buildings. Future versions of the guideline may have functional performance tests for commissioning and installation verification. As always, if you have any questions on Guideline 36 or how to specify it in your projects, please reach out to your local Trane account manager.
So that's our overview of ASHRAE Guideline 36. We hope you found it a helpful way to learn about this topic. As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic, or contact your local account manager for specific information on Trane systems, equipment, controls, and services. For those of you seeking continuing education credit, check out the newest online courses at our self-paced learning portal, and fill out a survey and let us know what you thought of today's program. Finally, ask your local host for details about upcoming E&L programs. Thanks for joining us today. We look forward to seeing you next time.